Okay, hello, we're back. We've learned the fundamental theorem of calculus, we got the basics, and then there were subsequent videos, which I called post-FTC day videos, which clarified, extended, expanded, whatever other synonyms, our understanding of the fundamental theorem of calculus, still at sort of a kind of a theoretical level, and these homework problems I think get at that a little bit. Page 329, I asked you to do two problems, 103 and 105. They were very similar to each other. And, okay, my thoughts on this over the years have changed. This seems like an extremely sort of ridiculous and artificial, intentionally sort of confusing, weird, kind of mathematician type question. But I no longer think that that's true. I actually think this is of big importance. And okay, what's going on here? Well, you are given some function, and the directions are find the derivative. Okay, so that's clear enough. But what's not clear is what this function is. And this is a function which is extremely, I think, difficult to understand. What's going on? Well, there seems to be an integral. So first of all, this is an integral function. And the function we seem to be integrating is the square root function. Yet, the upper limit of integration is not x, but sine x. Okay, so this is just strange. So first of all, we have to maybe take a step back and try to understand what's going. Make sure that we well, this is basically testing how comfortable we are with thinking of an integral as a function, or an integral function as a function. Okay, so I think the way to master this is to define a new function g, which is a little bit simpler. What is g? Let's let g be the integral from 0 to x of root t dt. Alright, that's already pretty complicated. This is what people call these accumulator functions. I believe they should be called integral functions because they are functions which output integrals. And if we want to really understand this, I think we did a good job on all the videos talking this out, but I'll just kind of try again. And if you don't need this kind of explanation, you can just watch on 2 times speed or not at all. What are we doing? We are integrating from 0 to somewhere under the root t function. So if we make a graph of the root t function, say here's 1, maybe here's 4, and so we got something like this. And this function is just going on and on and on. Okay, so first of all, do we know what an integral is? Yeah, I think we do. An integral is the limit of a Riemann sum, but it's also just the area under the curve. And so if I gave you some particular number, say g of 1, then what is g of 1? Well, it's just the integral from 0 to 1 of root t dt. Okay, so this is sort of like, our problem is like at sort of 3 levels of abstraction above this problem. Our problem is what's the derivative of this function? Okay, so simplifying a little bit, let's just consider this simpler function g. Well, it's also pretty complicated because it's an integral, but the true variable is the upper limit of integration. But if you plug a number into g, a specific number into g, like 1, then finally you get just an integral, which is itself complicated because it's a limit of an infinite number of subintervals and blah, 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 blah. But okay, if we're feeling okay about this, then this is just going to be the area under this square root curve. And okay, because I just know things, I know that this is going to be 2/3. We've in fact done this before. In other words, g is a function that, when you plug a number into it, outputs an integral, but an integral is a number. 2/3. When you plug a different number into g, say 4, then you get the integral from 0 to 4. And okay, in previous videos, I have tried to get you to believe that, well, okay, so now I'm going to go all the way to 4. I'll do this in a different color or something, I guess. So now this is like red or whatever. So how much is that? Okay, we could use the fundamental theorem of calculus. Somehow it's cooler or something to know that this curve, this square root curve, is really just like a parabola, a sideways parabola, and it's going to cut this 2x4 rectangle up into a 1/3, 2/3 type arrangement. And so I can just tell you that this integral from 0 to 4 is going to be 2/3 of 8. And so it's going to be 16/3. And okay, do I dare not double check that? I feel like we're going to be good because it's to the 1/2, 3/2, so 2/3 to the 1/2, and 3/2, I mean 8. Yeah, I think that's just right. So okay, great. What is G? It's why I think it's very important that we all should change our habits and call these integral functions is they're functions which take an input and then output an integral, which is a number. Okay, great. Then comes the fundamental theorem of calculus. And the fundamental theorem of calculus says that the rate at which this function changes is equal to the value of the square root function. In other words, going over here, well, okay, I'll just sort of state the fundamental theorem of calculus. The fundamental theorem of calculus says that G prime is going to be, otherwise known as the instantaneous rate of change of the integral from 0 to x of root t dt is just root x. And what this is really saying is that to just kind of explain this one more time, the sort of deep thinking behind this is, okay, if I want to know the change in the integral over some tiny period of time, then the change in that integral over some tiny period of time is just going to be the function times the small change in x. And if you have understood that this function is a function which tells you the area under the curve sort of so far, then if this is x, and I am asking for the change in this integral function, what I'm really asking for is, given a tiny, tiny, infinitely small change in x, so this becomes x plus, well, I'll call it x plus delta x, so some infinite, if you integrate out to some tiny, tiny, infinitely bit more far out, then what you get is a rectangle, and what's up with this extra little tiny, infinitely small rectangle? Well, the width of this infinitely small rectangle is delta x, and the height of this infinitely small rectangle is whatever the height of the function is at that point. And so since the change in this integral function is just the height of the value of the function times the change in the input, then we say that the change in this integral function, okay, we're getting way off track here, but maybe this is good. The change in this integral function with respect to the change in x is in fact just equal to whatever the height of the function is at that moment. And this can actually be made maybe more clear if instead of x we use 4. So la 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 and la 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 la. If we go out here to the point 4, and then at 4 on this particular function, I decide to increment my x value by some infinite tiny amount. Let's call that infinitely small amount delta x. Then we have a new point, 4 plus delta x. And when I ask for, if I ask the question g prime of 4, then the question g prime of 4 is asking, at 4, how fast is this integral function gaining new area? And the answer is that at that moment, at x equals 4, I'm adding these tiny new rectangles. And what are the dimensions of these tiny new rectangles? Well, they are delta x wide, and they are 2 high. And so the area of this new tiny purple rectangle is like 2 delta x. And so the derivative is the rate at which we are gaining area, and so for a tiny delta x, we are gaining 2 delta x more of area, and that's why it's very reasonable that g prime of 4 is in this case 2. Okay, so this is just sort of a re-teaching of the entire fundamental theorem of calculus, never mind the proof, but we're doing it for a particular function, and I also did something which I don't think I did in the video, which is talked about it at a particular number, at 4. Okay, and of course, if the formula is root x, then when you plug in 4, you just get 2. So everything's working out. Okay, what was the whole point of this? The whole point of this was to make sure that you understand very well what integrals are, what integral functions are, and what it even means to ask the question, what is the derivative of an integral function? And it should start to seem sort of now maybe kind of obvious almost to you that the derivative of an integral function just is the function. Because the height of the function describes, it sort of controls, so to speak, the size of the area of that infinitely thin rectangle that you're adding. And the answer, the area of that infinitely thin rectangle that you're adding is really the answer to the question, what's the derivative? Okay. All of that is fine. Now we have this new crazy thing, which is that now the upper limit of integration is not x, but is some other function. And so the simplest thing for you to do is to just realize that this is a composite function. And in fact, the reason why I think beginners should stop and construct a new function g is because it enables us to explain what f is. What's f? Well, it's just the g function, but with a sine x stuck inside of it, right? Anything you plug into g, the input to g tells you how far out to integrate. And so here, the answer is that we are going to integrate out to sine x. And this is just true, right? I mean, just plug sine into g, you just get this f function. Writing it like this, I think, helps cognitively recognize that this function f is the composite of two functions. The inner function is the sine function, the outer function is this integral function. And what you're really sort of doing is you're plugging a number into f, and you're evaluating the sign of that number, and the sign of that number, which is telling you how far out to integrate in the g function. Okay, so let's just push on. Well, now I think everyone just sees, if you didn't already, that this is just the chain rule. Because this is the composite inner function sine, outer function g. So what is f prime? It's, according to the chain rule, the derivative of g of something is g prime something back inside for the derivative of the something. And the derivative of sine is cosine. And so we're basically done. Because what is g prime of sine? Well, I've already calculated that g prime is root x. And so the answer is this is just root sine x times cosine. And if you totally get this, then of course you can just do this problem in 1 second by just recognizing that this is a chain rule situation. But I think there's some sophistication in getting to that point where this is sort of obvious. Okay. It's potential to even talk about this more by sort of getting... Okay, just really fast. So what if you're craving understanding of this picture, and what's really happening is, what you're sort of really doing, oh boy, is you're sort of saying, well, you're sort of saying, I have this function, and I want to, this is the root t function or something, and you're going out to the point sine x. And so what's really happening here is you're sort of giving me an input, x value. This is now supposed to be like a picture of f or something. F takes an input, plugs that an x input, plugs it into the sine function, gets an output of the sine function, And whatever that number is, that's how far out we integrate. And so if you dare ask the question, what is the derivative of this f function, this is the question we just answered, and you want to really try to understand this geometrically, I'm not even sure I totally can, but what we're doing is we're adding this sort of infinitely thin rectangle, but what are the dimensions of this infinitely thin rectangle? Well, I think it's clear that the height of this infinitely thin rectangle is root sine x. So that's nice. But here's where it gets complicated. The width of this rectangle is not so easy to understand because it's going to depend on the rate of change of the sine function. And so for a tiny change in x, what you actually expect is the, let's see, I guess what you expect is something like this. Cosine x delta x is really the best way of putting it, right? If I start my rectangle at sine x, and then you increment the x value by some sort of infinitely tiny amount, then how should I expect the sine function to change over that infinitely small time interval? And the answer is that the change in the sine function over some infinitely small time interval is just cosine, because cosine is the rate at which sine changes. And so if you, so if you sort of increment sine by some infinitely small amount, how much change do you get? You get cosine x plus delta x as the change. And that's why the width of this subinterval is cosine x delta x. And when you multiply these two blue things together, you're getting the area of this infinitely small rectangle. And yeah, okay. Good. Good. Unabridged version of analysis 1A you are getting this year, some of you. I don't think I've ever gone into that level of depth of that answer before. Not even one-on-one with a student. Okay, now let's see if we just know everything, and then the great thing about being smart is then you don't have to think anymore. We have some function f. What is it? It's the integral from 0 to x cubed of sine of t squared dt. Okay, you can do this problem in one step, or you can do it in like 3 steps. The 3 steps version, which I think is helpful, is to define a new function g, which is the integral from 0 to x of sine of t squared dt. We know that the derivative of g is, well, the derivative of the integral of a function is just that function. So the derivative of g is just going to be sine of x squared. This is the FTC. This is the deep way of thinking about the fundamental theorem of calculus. That the derivative of the integral of a function is just that function. Okay, and having done that, we may rewrite our f function. We may sort of recognize that our f function is just g of x cubed. And if f is just g of x cubed, then f prime is, via the chain rule, the derivative of g of something is g prime something back inside for the derivative of the something. G prime is sine of x squared, so when you plug x cubed into g prime, you're going to get sine of x cubed squared. So sine of x to the 6th times 3x squared, and that's the answer. And you can even just do that in one line if you're okay with that level of abstraction. All right, that was probably like a half an hour. Oh my gosh, 20 minutes. All right, we push on to other more straightforward problems, hopefully about which I will have much less to say. Yeah, this section was really all about substitution. And our book, you may have noticed, is kind of strange in that it sort of teaches you basic antidifferentiation, and then, contrary to the way we did it in my class, where I taught you all sorts of techniques of anti-differentiation. Now our book sort of is teaching us for the first time substitution. So this is a mixture of anti-differentiation by substitution problems and integration by substitution problems, which I personally think of as two very different things. Okay, so let's just sort of blitz through these early ones. This was just meant to be kind of a warm-up or something. You might feel that I am giving too many of these because you're like already an expert. So if you're feeling like you're an expert, that's a good feeling. If you're bored, that's good. It means you've mastered the material. Okay, what should we do here? I'll pull out a 5. And this is really like 1 minus x squared to the 1/3 times x dx. And I write it like that because it's just obvious to me what the correct substitution is. The substitution is going to be to let u equal 1 minus x squared. And then du dx is negative 2x. And so du is negative 2x dx. And understanding that that's the correct substitution, we just need a negative 2 in here. So I stick in the negative 2 and I undo the damage with a negative 1/2. And then this whole thing becomes negative 5/2 times the antiderivative of u to the 1/3 du. And now I anti-differentiate. And so this becomes negative 5/2 times, what's the antiderivative of u to the 1/3? Go up a power to 4/3, and you divide by 4/3. So 3/4 u to the 4/3 plus c. And so I guess this is just what it is, man. Negative 15/16 times 1 minus x squared to the 4/3 plus c. I'm not even going to check this. If it's wrong, then I will check. If it's wrong, people will cry. But I think I basically know what I'm doing, so it's probably right. Oh my god, it's actually wrong. What have I done? Did I make a embarrassing mistake? 3/4, 5/2. Oh boy. Baby's awake. 5x, 2, negative 2, under negative 5/2, u to the 1/3, 3/4, u to the 4/3, negative 15. Oh, just 2 times 4 is 8. Okay. Whew. Otherwise it was fine. Okay, 29, we do more. I somehow have some weird sense when the problem is wrong. Okay, this was an easy one, but you gotta know things. X squared plus 3x plus 7 over root x. The answer is that this is not hard. Whenever there's one term in the denominator, that's really good because it means you could split things up into pieces. So we just do algebra. This is really 3 separate problems. It's x to the 3/2 plus 3x to the 1/2 plus 7x to the negative 1/2 by just splitting the numerator up into 3 pieces and doing exponent rules with the x to the 1/2 in the denominator. So this becomes 2/5 x to the 5/2 plus that goes up to 3/2, and so it's 2/3. So it's 2x to the 3/2. That's just right. Plus, and that's up to the 1/2 divided by 2, so 14 root x plus c. Whew. Okay, 51. 1 over theta squared cosine 1 over theta. Okay, hopefully this was just blindingly obvious what to do here. It was to me. I let u be 1 over theta, otherwise known as theta to the negative 1. Then what is du d theta? It's negative theta to the negative 2. So thus we get that du is negative 1 over theta squared d theta. And that's just really good. because that's almost exactly what I have in there. So I stick in the negative and undo the damage with another negative on the outside. And this thus becomes negative cosine u du. And the antiderivative of cosine is sine. So this is just negative sine u, otherwise known as negative sine 1 over theta plus c. Sha. Okay, have we done with this yet? One more. 71 was, antiderivative e to the sine pi x, which our book doesn't do parentheses, it just assumes that you know by like default or something that this is intended. Okay, this is not hard because we see immediately that this is a composite function, that sine pi x is the inner function. So if I let u be sine pi x, then du dx is the derivative of sine of something is cosine something, but then back inside for the derivative of pi x, which is pi, and so du is cosine pi x times pi dx. Cha cha cha. All is good except for the pi, so I just stick in the pi, undo the damage with a 1 over pi, and thus we get 1 over pi times e to the u to u. And the antiderivative of the u is just e to the u, so this is 1 over pi e to the sine pi x. Probably could have just done that whole problem in your head, to be honest. Okay, cha cha. Good, making some progress. Okay, that was, those were 4 problems. All were just anti-differentiation problems. So, sort of mindless, and we've been doing this now for 2 whole weeks. I just gave you a million of those. So hopefully now it's just becoming obvious that it took some people longer than others, but everyone hopefully is at the point now where they can just basically do these, 90% of the time. So now we get to what I think is the new topic. The new topic is, although it's only slightly new, from a technical point of view, conceptually it's very new. What is the integral from -1 to 1? This problem says, number 95, of x squared plus 1 cubed. X times x squared plus 1 cubed. Okay, well now, why I say we're in a totally different world is, now this is an integral problem. And the integral, this is some polynomial, the integral from -1 to 1 is going to be a number, right? I'm not going to draw a picture because I don't feel like it, but there's some function, we have some rectangles, Riemann sums, blah, 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 blah. It's a whole crazy thing, but the answer to this problem is going to be a number. This is hard to do, though not impossible, but in general, it was hard to do. But with the fundamental theorem of calculus, one thing that's so great about the fundamental theorem of calculus is it turns all these problems into trivial little problems. Because really now, all I need to do is find some antiderivative of this. And the FTC says that if you know an antiderivative of x times x squared plus 1 cubed, then the value of this integral is just that antiderivative at 1 minus that antiderivative at -1. And so it's really because we want to compute integrals that we have forced ourselves to get really, really good at anti-differentiation, and we just are good at it now. So, okay. It's actually possible to just cube this using the binomial theorem and expand this whole thing out into one big polynomial and do it term by term, but it's probably like not faster. The fast way to do it is to recognize that if I let u be x squared plus 1, then this whole thing is gonna turn out great. And I'll sort of repeat what happened in the lesson a little bit on this. If u is x squared plus 1, then I should really think of myself, what I'm actually doing is I'm defining a new function u. Yes, it's just a variable transformation, but really, perhaps it's for some people more convenient to think of it as like a function. And if it's like a function, then when we take the derivative of that function, so u prime of x, you might say, then you get 2x but that's really just du dx. I'm just sort of cycling through all the different possible notations and showing this in different ways for different people if they like it, that du is 2x dx. Okay, so this is just exactly like what we've been doing for the last 10 minutes until I go to actually do it. Well, what am I missing? I'm missing a 2, so I'm going to stick in a 2 and undo the damage just like before. But it is at this moment that things kind of change, I think. Because, okay, it's true that 2x dx is du, and it's true that this is u cubed, so you do get u cubed du. But we are performing now, in my opinion, a substitution on this integral. In other words, we are transforming this integral into a new integral. And the transformed integral will have the same value as the original integral. But if we, since this integral is a number, I have to be careful. Think of this -1 and this 1 as telling me start with x equals -1 and end with x equals 1. But of course, if I'm now switching to a new variable, I have to switch those numbers as well. It's really just that simple. So what I'm now going to do is say that we're integrating from u of -1 to u of 1. In other words, I have to basically say, okay, plug -1 into the u function for x, and okay, well what you get is just 2. Is this going to be silly? I am so disgusted that I'm spending all this time on this problem because I see what's about to happen. I just got punked basically by number 95. But okay, I'll push on. When I plug in 1, what do I get? I also get 2. Okay, so before I realize that this is a stupid problem, which it is, because the answer is just 0, what's important is that when x is -1, u is 2. And when x is 1, u is 2. And so when I change my variables, I have to change my upper and lower limits of integration as well to get the answer right. Okay, this is just a dumb problem because, in fact, this function x squared plus 1 cubed is odd. This is an odd function because x squared plus 1 is even, okay? So if you take an even function and you cube it, that's like multiplying an even function by an even function by an even function, that's still even. But x is odd, and the product of an odd function and an even function is odd. So since this is odd, I'm sad because I wasted a lot of time talking about this problem. I should have just noted that it was odd, and since we're integrating from -1 to 1, any, make sure I'm not doing something wrong. Yeah, when I plug in 1, if I plug in -1, I get 8 times -1, so -8. So we're down here at -8, but when I plug in 1, I get 8, and this function is just odd, so this integral is just 0. And maybe I should have thought to look at that first. Oh well. 99 hopefully is a real problem. It is. Woo! Integral from 0 to